Okay, so start off, I'd like to review what I did in chapter 5 before spring break. Since it's 2 weeks ago, I figure it's probably worth a review for all of us. So in the last chapter, in chapter 4, we focused on pure substances. So cases where C equals 1. And in this chapter, we're going to be looking at binary mixtures. So now C equals 2. And as we talked about back in chapter 1, if you have a mixture of more than one gas, each gas can contribute to the total pressure of the mixture of gases. And the contribution of each of the constituent gases is called the partial pressure. So we're going to look at some more partial type quantities because we're talking about mixtures and what each constituent contributes to the mixture. So the first one, in particular, we're going to be talking about molar quantities, partial molar quantities. So the first one that we're going to look at is partial molar volume. So the partial molar volume is defined to be of a substance A in a mixture. It's defined to be delta V of the mixture, change in the volume, when 1 mole of substance A is added to the mixture. And here we're assuming that the mixture already has a large volume. If you add substance A to a small amount of the mixture, then it's not going to behave the way that we want, because you can just imagine if I pour a lot of water on top of a little bit of ethanol, I'm not really going to find out what happens when the two mix very well. So we're assuming there's already a large amount of the mixture. Okay, skipping ahead a little bit, let's talk about the definition of partial molar volume. So for a substance J, the partial molar volume is defined to be the derivative of V with respect to Nj. So that's the change in volume per mole of substance J that we add or remove. And when we do this, we're keeping the pressure constant, we're keeping the temperature constant. And this N prime means that we're keeping the amounts of all other substances in the mixture also constant. So if you were to plot volume versus number of moles of substance J, then the partial molar volume is the slope of that plot at some point N for the number of moles of J that are present. Notice that partial molar volumes, volume is always positive, but partial molar volume is the slope. And so it can be negative even though volume is always positive. Okay, moving to the next page in the notes. I posted these notes on Canvas. Hopefully you saw the email about that. But moving on to the next page, binary mixtures. So we're going to be talking about binary mixtures, and we're going to label the two components of that mixture, A and B. And so now suppose we change the composition of the mixture. So we're changing the number of moles of A by some small amount, and we're changing the number of moles of B by some small amount. So what's the total volume change, dV? So as we've talked about before, if I want to write the differential of a function, in this case, the function is a function of Na and Nb, the number of moles of the two substances. So if I have a function that depends on two variables, and I can write the differential using basically the chain rule, where dV is equal to the derivative with respect to one of the variables, Na, times the change in Na, and plus the derivative of V with respect to Nb times the change in the number of moles of B. Now here you see that we are holding pressure temperature, and the other substance, the amount of the other substance, are held constant in each case. And if you look at this, it's pretty clear that what we've done here is we've written the partial molar volume right there. So dV is equal to VA, where VA is the partial molar volume of A, dNA plus VB, the partial molar volume of B, dNB. And then we can integrate both sides of this equation, and we wind up with an equation like this. So here we see the contribution of each component to the volume. Component A, the molar volume, that's the volume per mole, times the number of moles gives us the volume that that substance A contributes to the total volume, and likewise for substance B. Okay, so that was a quick review of what we did on our last meeting before spring break. So now I'd like to move on. Still in section 5A, and we're going to talk about another partial molar quantity. This one is the partial molar Gibbs energy. And you can probably guess already how this is going to be defined. So it's going to be the change in the Gibbs energy when we change the amount of a particular substance, say substance J, and this is holding pressure, temperature, and the other substances constant. And it turns out that this is the definition of chemical potential for substance J. Now, this is not the definition that we've seen before. And the reason for that is because we were looking at a pure substance before. So remember that for a pure substance, let's take a look at that real quick. So I can write the Gibbs energy of a pure substance as equaling the number of moles times the Gibbs energy per mole, the molar Gibbs energy. And that's for a pure substance. And if I now apply this definition that I wrote above, I'm taking the derivative of G with respect to N. Take a look at my formula for G. What happens when I take the derivative of this with respect to N? Well, the N goes away and I'm left with GM. And this is exactly how we defined the chemical potential before for a pure substance. So now we're using mixtures, and so we need a more general definition for the potential, the chemical potential, and that's given by this equation. Okay, so added a few notes here. One nice thing about doing this with a document camera is that I can take these papers and scan them and put them online for you. So you don't have to write all this down, although you're welcome to take notes. So let's take a look at what this would mean on a graph. So we're talking about a derivative. So again, we're talking about a slope. So if I graph G versus the number of moles of substance J, and I'm just going to make up a curve here. Then at some given point, there's some amount Nj, the partial molar Gibbs energy, or the chemical potential, same thing, those are synonymous, is given by the slope at that point. And if I pick another point, I might get a different slope. Okay, now let's take a look at G for a minute. And let's say that G is a function of the number of moles of some substance A, the number of moles of some substance B, and so on for however many substances we have. Okay, if those are the variables that G depends on, then we can again use this chain rule like formula to write dg. And dg will equal the derivative of G with respect to Na times d in A plus derivative of G with respect to NB, dNB plus, and so on. And if we take all of these to be at constant pressure, temperature, and prime, so I can put that this is at constant temperature and pressure over here also. Then we see that we have the definition of chemical potential right here. So we can write dG is equal to, this is the chemical potential of species A, DNA plus chemical potential of species B, DNB plus, and so on. Okay, and just like we did as before, we can integrate both sides of this equation, just as we did before for partial molar volume. And we get G is equal to Na mu A plus Nb mu B, and so on. Okay, so why is this equation useful? This is, if you recall, the what your book calls the fundamental equation of chemical thermodynamics. So this gives us the change in G if we were to change P and T, temperature. Okay. But looking up here to this equation, we see that there's another way to change G, and that's by changing the amounts of substances involved. So previously, when we derived this equation, we were holding the amounts of all the substances constant. But now we have another way of changing the Gibbs energy. So I'm going to combine these two. So we have a more complete formula for dG. So dG is going to be VdP minus SdT, like it was before, plus mu A dN A mu B dNB, and so on. So we can change the Gibbs free energy by changing the pressure, by changing the temperature, or by changing the amount of any of the species that are present in the mixture. And then you can see, of course, if we hold the amounts of substances constant, then all of these dN terms are zero, and we recover the original formula that we've been using before. Okay, now let's take a look at what happens to dG if we hold P and T constant. So now the dP and the dt terms go away, and dG is going to look like this, which again recovers the equation that we saw on the previous page. Okay, so if you recall from chapter 3, if we hold P and T constant, then the maximum amount of non-expansion work, which we called additional work, is equal to dG, which means it's equal to this formula that I wrote up above. Okay, so we have this formula for the additional non-expansion work. And what's interesting about this is that work can arise just by changing the composition of a system. So just by changing the number of species, different species that are present. A good example of this is an electrochemical cell. We get electrical work out of an electrochemical cell, and that's a result of the fact that inside the electrochemical cell, the composition is changing as products are formed from the reactants. Okay, so I've summarized that here. And now I'd like to talk some more about chemical potential. And we're going to be using and talking about chemical potential for all of chapter 5 and 6, basically. And I'm going to show you why it's so useful here right now. So as we've discussed, chemical potential is derived from the Gibbs energy. So let me return to the definition of the Gibbs energy first. U plus PV minus TS. And I'm going to rearrange that. I'm going to solve this for U. And if I do that, I get minus PV plus TS plus G. And from there, now if I take the differential, I'm going to have to use the product rule on several of these terms. So if you'd like to try to do this yourself. Use this formula for U and find the formula for DU. You can pause the video real quick and try it. And I'm going to do the same. I'm going to pause my video and I'm going to write it down. Okay, is this the result you got? The first two terms come from taking the product rule on the PV, and the next two terms come from taking the product rule on TS, and then we have DG. Now, we just talked about the formula for DG. So let's plug that in. And I mean the more general formula that we just came up with. I'm kind of running out of space. And when I do this, you can see that there's some cancellations. For one thing, this VDP inside the DG is going to cancel with the minus VDP outside. And likewise with this minus SDT inside the DG, it's going to cancel with SDT outside. All right, so that leads us, after cancellations, to this formula for DU, minus PDV plus TDS, plus mu A dNA plus mu B dNB. And this is very similar to the fundamental equation that we've seen before, which was minus PDV plus TDS. So you can see that this new equation is an extension of our former fundamental equation. Okay, now let's take a look at what happens if we hold V and S constant. If we do that, then this dV and this ds term go away, and du is equal to mu A dNA plus mu B dNB. And this looks very familiar, and so on, because this looks just like the formula we had for dG. So once again, looking at if U is a function of these NA, NB, and so on, then du is going to be the derivative of U with respect to NA times dNA plus the derivative of U with respect to dNB times dNB, and so on. And here we've held V and S constant, volume and entropy. And then of course we're also holding, when we take a partial derivative with respect to one of these n's, we're holding all the other n's constant. And if you look at this, you see that right here, is our formula for the chemical potential. And the reason we know that this is the formula for the chemical potential is because I'm comparing this equation for du and this equation for du. You see what's in front of the dNA here is mu A, and what's in front of the dNA down here, therefore, must be mu A. Okay, so as I was saying, by comparing these two formulas for du, we arrive at a new equation for the chemical potential. So the chemical potential of species J, say, is equal to du dnJ. And this time we're holding entropy, volume, and the other amounts fixed. So this gives us some hint to the power of the chemical potential. Before we saw that the chemical potential would tell us how much G, the Gibbs energy, changed if we change the species present, the amounts present. And now we see that the chemical potential also tells us how much U will change if we change the amounts. The difference being, of course, the things that we're holding constant. Okay, so mu tells us how both G and U change when substances are added or removed. And G and U are two of our thermodynamic potentials. So could we do this for the other thermodynamic potentials? H, the enthalpy, and A. And the answer is yes, we can. We can follow the same exact argument, and we come up with 4 formulas for the chemical potential. One for each of the 4 thermodynamic potentials. Okay, so we get this result. Any one of these can be equated to the chemical potential. So the chemical potential is telling us how each of these thermodynamic potentials is changing as we change the substances, the amounts of substances that are present. The difference being, besides the different thermodynamic potentials, is in what variables we're holding constant in each case. So from this, I hope that you can see how central the chemical potential is to doing chemical thermodynamics, which is why we will be spending so much time on it in this chapter and the next. Okay, I still have more material to cover in 5A. I'm going to stop this video here just to break it up into some smaller chunks that are a little easier for me to record and for you to digest. So I will stop here, and I'll see you in the next video. We're going to continue with section 5A.